Okay, so Gauss's law is the following. Basically, it says if you take a surface and look at some point on the surface, make a small area around that point, delta A, and look at the electric field at that point. Let's say it's pointing in some direction. Take that electric field and look at its components. The component that is perpendicular to the area and the component that is along the area, E parallel. So what is the purpose of doing this? We want to understand what is the net flux of electric field lines coming out of the surface. So let's take another area here, and again we want to understand what is the flux coming out. So if the electric field is pointing in this direction at another point, we again take its perpendicular piece and multiply E perpendicular with delta A and do this over all portions of the surface. Sum it over all the little delta A pieces, and Gauss's law says that that summation will be equal to the total charge enclosed divided by a constant epsilon 0. So let's apply this to a positive charge. So if I have a positive charge here, we have already seen that it creates these contours of constant potential, and the electric field at any point P here points outward, radially outward from that point P. So if I take my Gaussian surface, so this is an important point of using Gauss's law. If you can use symmetry, you can greatly simplify the calculation. So in this case, for a charge, it has spherical symmetry, which basically means the surface I take is a sphere and or a shell centered at a shell with a radius equal to r. Now on this shell, I can take these little areas since the electric field is constant at every point given by kq over r square, but it's the same magnitude at every point regardless of where I am on this spherical shell. Even though its direction is changing, the magnitude is the same for E perpendicular. I can write this summation E perp delta A equal to E perp comes out of the summation, and I only have to sum up delta A. This is just the total area of a spherical shell. And that, as you know, is equal to 4 pi r square. So from Gauss's law, what we get now is E perp times 4 pi r square is the charge enclosed, which is the whole charge q here, divided by epsilon naught. And that gives us E perp is equal to q over 4 pi epsilon naught times r square. This is nothing but our familiar constant k, q over r square. And k is equal to 1 over 4 pi epsilon 0. So that's how we can very quickly get the electric field for a point charge.